Swayam Prabha. Digital India. Educated India.
Hi students, hope you all are doing well. Welcome to another exciting session of the course Soft Tissue Characterization and Applications. So we were talking about the different techniques and modeling methods in the finite element software ANSYS. So let us continue on that and learn a little bit more into the other topics which are important to get to that point where we can model and simulate all sorts of soft tissues. So let us get started. Okay, so this is where we were. We had developed a sample model with a particular wound shape. This wound geometry was created through the bottoms up approach, and then we had basically created a set of splines, and based on that the area was subtracted from the almost the rectangular area, and then we had extruded the entire sample. So we had learned about all the modeling techniques, the operating techniques, how to do the meshing. So right now we are focused on understanding through a mesh convergence study that how to make sure that there is a mesh which you select which can give you accurate results. We do not want the mesh to affect the results at all, right? So that's the goal in any of the simulations, be it on a very highly nonlinear simulation with an organ, or you're doing a very simple simulation. You want to make sure that your results are legit, right? So in order to do that, we need to perform the mesh convergence study. Okay, so let us do that. So we will continue from here because we already have the model, so I'm not going to remake the model any further, but I'm just going to show you what the model looks like one more time. So we had a bunch of key points here which shows the basically the cuboidal volume with the wound volume which was extruded, right? So if we look at the plot lines, we can see the lines, however, with certain kind of a dash pattern showing that the meshing has been done. That doesn't visualize anything else, right? So this is good. Then we can plot the areas, plot the volumes, right? And finally you plot the elements, right? So we do have some form of elements. So we just started learning about some of the element control techniques, right? Using the technique smart sizing, which I've said like it's not a very good technique per se, because it doesn't give you any signs or a strict control on how many elements would you want, or where exactly would you want to refine the mesh. So what is mesh refinement? So whenever you have sharp corners or edges, those edges need more elements to be fit in there in order to make sure that the results are accurate. If you fit in a huge element there, it is not going to give you an accurate result. So here is an example where basically on the edges you are looking at the broad edges, you are looking at big elements, but whenever you are moving towards the sharp edges like this one, you are looking at much more smaller elements. This is an automatic refinement which the computer does, but you can control that refinement to look at how much is the amount of refinement would I want, right? So this is the thing which we are talking about, and we went to mesh tool and we basically learned about the smart sizing, also the global sizing control. The benefit of the global sizing control is it allows you to break down any of the model or geometrical model edges mean any of the lengths and dimensions, into multiple segments and build the elements based on that, right? So we learned how to divide every line or every edge here by 10 divisions or 5 divisions, and how to apply the meshing then to get the right mesh. But the problem with global is it doesn't allow you to independently select certain lines and apply certain refinements to it. it uniformly applies the refinement to all the edge lengths. So irrespective of whether the length of your geometry is like 10 millimeters versus 2 millimeters, it's going to still divide it by the factor of 5 or 10 if you apply a factor of 5 and 10, right? It's not going to selectively do that, right? So we want to be more selective, and in order to do that, we want to apply the lines based sizing control, which is usually very handy and useful, right? So before I do that, I want to do start an exercise which is part of the mesh convergence study, and then I'll show you an example from literature. Literature is something which is a published work where we also do the mesh convergence study, right? Very similarly. Okay, so let us look at few factors. So I've opened a PPT here. So in this PPT, I have the one blank page, and I have also opened an Excel. I'll show you what the importance of that is, and I'm also going to make the background as this with the reverse video white, right, so that I can take the pictures in a better form, right? So this is my first. I'm not going to move this mesh. I'm going to keep it this way, right? So also let me take out snipping tool, right? That way I can snip some pictures. Okay, so let me snip this first picture, right? And I'm going to throw this into the PPT, right? This is the first picture, just to have a comparison standpoint. Okay, the next thing which I am going to do is I will learn about the number of elements which this particular model has. This is using global sizing controls, what I did, right? So let's take a look. So what are the number of elements? If it is very high, we'll probably neglect that. Yeah, this is 11,000. So we are probably going to neglect it. So I'm going to take a different mesh rather than this. So let me just delete the global sizing control, clear it out, and remesh this guy using a standard mesh. And that creates a standard mesh, right, with some warnings, with of course no smart sizing or nothing on. So that's good to go. So I'm going to take a picture of this mesh rather, because I am going to slowly stepwise refine that and look at the results. That's the thing which I'm focused on, right? I want to slowly and steadily keep on refining the mesh and look at how the results change, and then find some conclusions that where the results have stopped to change by that much amount which it was changing earlier. That is where we can find the optimal mesh which is useful for further analysis, right? So let us look at the number of elements. So 537, this is a decent number, so I'm going to write that down here. So let me just open up a text box. I'm going to write down a few things. So element is ELEM 537, right? I'm going to also write down the DMX, which is the maximum displacement, and stress max, right? So these values I'm going to write down from the simulation. The next thing which I'm going to do in order to start my mesh convergence study, so we are going to learn the sizing control and the mesh convergence study together, right? That way we are saving time here. So this is the first mesh. So I'm going to go ahead and apply a load and boundary condition or a constraint here and fix that constraint and not change that. I'm going to only keep on changing the mesh and look at the results. Okay, so that's the goal. So let me apply the loadings here. So structural displacement. So let us apply a loading which you would expect in a universal tensile testing based mechanical test, right? Typically the bottom would be constrained and the top would be pulled. So let's apply such a loading. So I'm going to constrain the bottom area in all degrees of freedom, right? And then I'm going to apply, I can not only apply pressure, I can also apply a certain displacement to the top, right? That can also be done. So I can apply, let's say if this is of 5 millimeters, I can easily apply, let us apply a displacement load this time, just for variety. So I am going to apply what kind of displacement along the which direction. This is very important. So let me just see what my directions are. Okay, just 1 second, this thing should be clicked. So I just want to make sure what my directions are. I cannot see them. So I'm pointing towards X. So I'm going to apply a displacement in the direction of X. Okay. Hopefully this view is almost similar, right? I want to keep the view same because so along the UX I want to apply a displacement of 1, right? Along the positive X, so it's going to pull it. So the yeah, positioning is almost similar, so I'm going to keep it this way so that I can click more pictures. Okay, so the loads and boundary conditions are done, right? So I've applied a constraint on the bottom, I've applied a displacement load on the top. Now I'm in a position to run the results, right? So analysis type, new analysis. Let us solve this. Takes a few seconds. Done. So I go to general post processing, plot results, deformed shape, undeformed edge. There is of course deformation. What I'm really focused on is the result viewer, so I'm going to stick to this. I'm going to straight on look at stress and I'll get the value of dmx there as well, right? So this is a stress distribution, right? So let me see what the dmx value is. It's 1.00333, so it's almost like 1, right? Because I've applied that much amount of displacement. So I'm going to write that down. I'm going to just keep it as 1 because the amount of that is much places in the decimals, that is not to be considered. So what is the solution max? We are looking at a 724.017. I'm going to ignore the decimals here because they are very small in comparison to 724. So let me just put it as 724 for now, and I'm going to see the change in the result as I change the mesh, right? So 724. So this is my mesh number 1 which I work with, right? I'm going to close out of this. The next thing which I want to do is I want to come back to the elements. Everything stays the same, the loads, boundary conditions, everything stays the same, that doesn't change. Only I'm going to change the mesh. So ideally it should give us the same solution, right, irrespective of the mesh, because mesh is just a operational tool, right? Like it is just going to mesh that, and if you apply so much loads and boundary conditions, it should give you the same result irrespective of the mesh. So that is what we are going to check out now. Usually that is not the case, right? So let us go to meshing, mesh tool. So what I'm going to do next is I'm going to apply some sizing controls which are line based sizing controls. So right now what I'm seeing is 1 2 3 4 almost 10 divisions. So I'm going to do something similar. So under the set option, under line sizing control, I'm going to set all the longer lengths here, right, all these 4 guys to 10 divisions, right? And you can apply this sizing control multiple times to different lines, right? Not in the case of global because you're applying to everything, right? Here you can apply to different lines separately. So I'm going to put it as 10 divisions. Okay, done. Now I'm going to go to sizing control one more time and set the other smaller lines, these guys, maybe to 2 divisions, right? Done. Then I want to set these lines to 5 divisions. So am I done? Not yet. So I want to also set these lines to 2 divisions. Okay, there are lines here also. You can do many of them together if the number of divisions are the same, but you can do them separately also. Then the last thing left is I need to still figure out this one, how they are going to be divided. So there is one spline here, one spline here, one spline here, one spline here. How do I want to divide them? So let me divide them by maybe 5 divisions, right? they're a little wide, they'll open up to be at least as big as this. So I want the mesh to be as smooth as possible, right? So the goal is we do not want a mesh which has a huge element followed by huge amount of smoothing where this mesh is very smooth. So we want a nice transition from the larger elements to the smaller elements, right? So I'm going to break this to 5 divisions, right? Okay, done. So what this will do you is, if you are looking at the lines, it will show you exactly based on the divisions kind of how the lines are, but that's just visual. So let's go back here. So now I'm going to, now all the lines are set through sizing control. I'm going to apply regular meshing to this and see what happens, right? Something happened. So what are the number of elements here? 881, right? 881 is the number of elements, right? So this is not very different from 537. At least we want to go like a few thousands into it, right? So I'm going to neglect this one and clear out all the sizing controls here. If I hit clear and pick all, it's going to remove all the sizing controls out of the system together. So I'm going to reapply this sizing control, maybe make the divisions a little larger, 1, 2, 3, and 4. Maybe make them to 12, right? And I want to apply the sizing controls here, 1, 2, 3, 4, 5, and 6, right? These are all similar. You maybe this can still stay right, maybe 3, so 12, 3. Then I want to apply the sizing controls to these folks, keep them as 5, maybe a little higher, 6, multiples of 3, that's okay. And last thing is I want to apply sizing controls to these guys, also put them as 6, right? I could have done them together along with it. So all the sizing controls are good. Now I go ahead and remesh this. Do you want to remesh? Yes. So there has been some remeshing. I can see some large and smaller elements, so it may not be the best mesh, but let us still see what the number of elements are. So it is around 1393. This is okay, we can consider this 1393. Okay, so I'm going to take a quick snapshot of this mesh, right, and place them side by side over here. Right. I'm going to also make this guy maybe just a little bit of, yeah, this can be better. I'm going to just copy paste this guy, a little gap, right? How much was it? Like I forgot, 1391 most likely. Yeah, just recheck if you forget. 1393, yeah, 1393, right? I want to also look at the solution. So all the loads and boundary conditions stays the same. So I'm going to just go ahead and run the solution. Just make sure you click the analysis type in new analysis. So this is done, and just solve it, right? Done. So I'm going to go straight to the result viewer, right? Because I'm only interested in learning about the stress and the maximum displacement. So this is set by default, right? Okay, so what has changed now? The result has become DMX is still 1, which is good, but the SMX, which is the solution max for stress, has become 779.989, almost close to 780. So I'm going to write that down, right? 780, DMX stays. So it has increased quite a bit, right? Like almost by 55-60 points, right? So that is how these, but you can see the mesh refinement very clearly when you put them on parallel to each other. In one you can see the wound as kind of approximated by very large elements, and here the wound shows much more descriptively, right? So okay, so let's go back and do more. We are at least going to do like 6-7 meshes, and then we will have some conclusions, and there is no bar to it. You can keep on doing like 10 or 15 meshes. The thumb rule here is we have to eventually go beyond 10,000 elements. That is the sweet spot. So typically your results tend to converge well after 10,000 elements. Sometimes it doesn't converge till 20,000 for very complex models. So we'll find out, right? So let's do this. So let's go back to plot elements. I'm going to just remesh this guy, right? So mesh tool. So first of all, I'm going to remove all the sizing controls, right? And then I'm going to redo the sizing controls. Last time I had multiples of 3, so this time I'm going to make it a little bit more, so maybe 15, right? And you'll be surprised to see how drastically the elements change, right? Increase. So these guys 1, 2, 3, 4, 5, 6. Right? So they were divided by 10, I believe 3. So we are going to make that 5, right? Multiples of 5. That is how I can remember. So then I'm going to set the lines. These folks 1, 2, 3, 4, and 5 and 6. Right? You can select all of them if the number of divisions are the same, and I'm going to change them to 10, right? Rather. Okay. So this is most likely going to produce a lot of elements, but let's find out. So I'm going to mesh it normally, right? Let's see. Not a drastic amount, but let us find out what the value are. So we are looking at 3251 elements. Okay, 3251. Good to know. So I'm going to take a snapshot of the mesh. Right, I'm going to just recopy. 3251 was the number. So 3251 elements. Let's find out what the solution is. We haven't ran that yet, right? So analysis type, new analysis, right? Done. So fairly simple and straightforward. You are just modifying the mesh and looking at what the solutions could be and whether that is changing, which we are going to find out in detail as we go. The stress, this is selected by default. Just double select this. So now the results have changed drastically, if you can note here. So the DMX still stays very small, like to 1 only, but SMX has changed to 914.484. I'm just going to assume it as 914.5, right? Subjected to 1 place of decimal, right? Approximated to. So 914.5. So quite a lot. DMX still stays 1. So we see the mesh improving, but we do see it is improving with some issues where the results are fluctuating a lot, right? So this is something which is not desirable. That is the reason we are conducting this mesh convergence study. We want the mesh to be accurate. The results should not be changing due to the mesh. It is a little bit of a hit and trial technique, so there is no clear path on whether you should take 5 meshes or just increase the elements by this time. There are some rules of thumb, like you want to increase them by certain intervals, and usually beyond 10,000 is when the results tend to converge in most simulations, right? So we'll do that. So okay, so we go back to where we were. So we go back to the elements, and we are going to do the sizing control one more time, and before that we are going to delete all the sizes. Right. Okay, so I'm going to set these tall ones in the multiples of 6 now. So I'm going to make them 18. Earlier I had 15. Then I'm going to make these guys is 12. Right. You can do them in any order. And these, oops, my bad. You can unselect, by the way, by clicking your right click or clicking at unpick, right? So this is my unpick button, pick, unpick. So this is something wrongly I've selected, so I'm going to unpick. Oops. So, okay. So these ones will go to 6, right? Multiples of 6. Done? Okay, now let us mesh it. Yeah. There is some shape testing warnings, which means that there is something we are not doing very correct in terms of the mesh. So I might have to refine this little more. So I'm going to just check quickly what the elements are. So this number is good, 8160. Okay, so I'm going to take a small snapshot. Placing them side by side is very important, otherwise we do not know what we are comparing and how we are comparing, right? So that becomes really important. I'm a little finicky with the positioning and all that, so that's the thing. So okay, so what are we looking at? How many elements was it? I think 8160. Yeah, 8160, correct. Right. So I'm expecting the DMX to stay the same, but the results to drastically change. So let us run the solution. Right. Solve. So you typically see, once the number of elements increase, like the amount of time which it requires to compute your simulation increases quite a bit, right? Okay, so we are looking at much higher values. 1013 point, I'm going to consider it as more towards, so 1013.7 is okay, and DMX still stays the same, 1013.7. Okay, perfect. All right, so you can see the mesh actually refining. That refinement can be easily seen. So let us go further. We need at least 6 to 7 meshes too. Okay, so now I'm going to clear everything again. I'm going to just repeat this activity a few times, right? So let me make this a little better. So now in the multiples of 10 maybe. So I'm just going to make this 20, right? So then maybe I want to make these a little less, not these many. So these were 6. I think 6, 10 would be too high. So typically what happens is, if I increase them by the same ratio, that's not the rule of thumb. I should typically increase them in the ratio of in which the lengths are, right? So this length is much larger than this. So dividing this by 6 points is actually causing the elements to increase in certain places. So the aspect ratio which we talk is very important. So we should not divide a small edge by a very high number of divisions and the longer edge also by the same number of divisions. That's why we are getting the warnings, right? So I'm going to just divide these guys by 5 divisions only. Right, that should suffice, I think. And this one in aspect ratio seems like 1/3 of this almost. So if I'm doing a 20, I could safely do like a, not that high, I would say around 7 or 8 at the max. So let me put this as 7, right? Twenty-five 7. This is what I did. Okay. All right, let's mesh this. Much better meshing, right? So let's see what it has led to. Basically, number of elements. Oh, it has decreased the number of elements. So that is something we do not want. So we want the elements to increase. So I'm going to just redo this one more time. Because if the elements do not increase, we cannot perform the mesh convergence study. So I'm just going to make these guys maybe to, I think 20 here is okay. These ones can be a little better way done. Oh, I did a mistake there as well. I selected this edge, but the other edge on the other side was not selected. So that's a mistake, right? Hopefully you understand what I mean. It's these two set of edges. I mistakenly selected just one set, right? So the other side will end up having large elements and one side will have like smaller elements. That's not desirable, right? I'm going to give it a little bit more, maybe if that is 20, maybe like 8-ish. Yeah. So they're all distributed by 8-ish. And then I want to break these folks by maybe 6-ish. 28-6. This is what I'm going for. Let's give it a shot. Yeah, there is some issue, but anyways, yeah, it's just increased to 4,700. You want to increase it further. So let me do this. Let me clear this one more time. And let us set this guys a little higher. Maybe I'm going to make like 25, right? 25. Then I'm going to put these ones as 2, 3, oops, not this, 3, 4, 5, 6. 6 can go to around 10. Yeah. And these folks 1, 2, not this, 3, not this, 1, 2, oops, I'm going to reset this. I forgot what I did. So 1, 2, 3, 4, 5, 6. I'm going to make them like around a little higher, 8. 25, 10, 8. Let's do this now. Should increase the elements. Okay, so I see a much more refined mesh. I'm expecting at least the elements to be much higher, right? Let's see how many. Yeah, this is good. 12,762. So this is a mesh I can consider. 12,762. 12762, right? You can clearly see the mesh has refined quite a bit. This is a very important exercise to do a mesh convergence study. That's why we are spending our due diligent time to do this, right? So this is done. Takes a minute. Okay, let's go straight to the result viewer. Okay, so you see quite a bit difference in the result. DMX still stays the same, and this increases to 1186.16. 186.1, which is okay, which will go to 1186.2, which is fine. So we have now overshot 10,000, but we don't know whether the mesh has converged, so we are going to increase this a little further, right? Do a few more meshes. Oops, no. Okay. Plot elements again. Let us clear this. So we had 2010.8 last time, right? So we are going to set this, sorry, 2510.8. So we are, I'm going to set this a little higher. Yeah, I'm going to put like a 28. Then this was 10. Right. Oops. So let us divide it by proportionally. Yeah, so let us divide it by proportionally by that one. So we were dividing the other one by 28, so this has to be divided by at least 1/3 of what we are looking at. So maybe we selected 10 last time, so we can maybe go to 14 or something, right? I'm just going to go to half. So done. Okay, next is we have to select these folks. Yeah, so let's divide them by maybe 8 points. 8 points is okay, not 18. 8 points. So once we are done with this, let's redo the meshing. Yeah, we are seeing quite a bit of mesh, so let us see what the value of the elements are there. Quite high, 19,750, quite a good bit of jump. With just a few number changes, the numbers have jumped quite a bit. So 19,750. Let me take a quick snapshot. Right. $19,750 is what we are looking at. So now let us run the solution. Take a few seconds to do that. Right, done. The number of elements are increasing, the solution time is also increasing. That is very clear, right? Okay, so the von Mises stress 1194.83, right? So what do I observe here? As the number of mesh element increases from 12,762 to 19750, the stress value has not increased drastically. This is the point where I can possibly stop. right? So it has not increased drastically even with the drastic change in the number of elements. So this is where I can stop my mesh convergence. You might have to go further, like depending on the kind of model you're working on. So there is no same rule which applies for all the models, but the thumb rule is wherever you're seeing that even with a drastic change in the number of elements, the value of stress or the displacement is not changing drastically, that is where you can possibly stop and we can do further analysis. Okay, so let us just take a very clear look on this, on a broad look, how this looks like. So these were the meshes, and we went from here on the left to all the way on the right, and we can clearly see that the meshes are getting much and more refined meaning the number of elements are increasing. So we have gone all the way from 537 to 19,750, right? So which is my optimal mesh here? Which is the mesh should I I should ideally select? Right? Optimal mesh is, by definition, the mesh with a particular number of elements beyond which the results do not change drastically. That is the basic definition, right? So let us take a quick look at these meshes. We are seeing that the DMX almost stays the same, but the stress values keep on changing. So now let us go to Excel, and we will understand a few things, right? So in the Excel, I am going to plot number of elements, right? So this is my column 1. Then I am going to plot DMX, right? Then I am going to plot stress max, right? These are the values I am going to see, right? Then I am going to find out percentage difference. So how much do the values differ? So let me just take a quick snapshot. What I'm going to do here is I will take a snapshot of these guys and copy paste it. It's easier for me to fill in the data rather than go back and forth. So I'm just going to take a snapshot of this, and in this I'm going to copy paste this, right? So and reduce the size a little bit, that way we can all see very clearly what I'm trying to do with the mesh convergence, right? Maybe a little larger. Yeah. Okay, so let me write down the number of elements. This is 537 followed by 1393 followed by 3251, 8160, right? 127 62, right? And then finally in 19750, right? What are the values of DMX? It has not changed much, so I can just do 1 and just pull it all the way down, right? Okay, what is the unit of DMX? This is also important. This is in millimeters, right? All our measurements are in millimeters, and all our stresses are in megapascal, MPa, right? So what are the values of megapascals? So we are looking at 724, right? Followed by 780, right? Followed by 914.5, right? So you may ask that, for example, this 724 and 780 is not very different. Why didn't we stop here, right? This could be a question. So the reason we did not stop here is because this amount of change, 55 points almost, is a huge change for just a few elements changed, elements which we have smoothened, right? Like, so we have gone only from 537 to 1393, and the results have changed so drastically. But here this is not the case. In the very end, we have almost doubled the results, like by 10,000 elements we have increased. Still it has not changed, right? So that is of concern. That's why we have not stopped here. And also visually, if we look at, we would like to see at least some level of smoothing, like at least the level of the 4th or 5th or 6th mesh, right? Like not before that. So there are some visual rules of thumb as well, right? So this is 914.5, this 1013 7, then I'm looking at 1186.2. So always go for 6 to 8 meshes at least. That's the rule of thumb. Here we are looking at 6 only and we could figure it out, but minimum is the 5. Never do below 5 meshes. And with the meshes you have to always have at least some meshes which have number of elements beyond 10,000. These are the thumb rules, right? 1194.83, 0.8. I'm going to write it to that place of decimal, right? Okay, so what is the percentage difference? This is how you find out. So it starts from the second one. We want to look at what is the percentage difference. So percentage difference in what? Percentage difference in stress max, because dmx is all constant, right? So how do I find percentage difference? So this is the change. So I have to do this one is equal to this one minus this one, right, divided by this one from which it has changed times 100. This will give me the percentage. I'm going to take this down, right? So and just double check, C4 minus C3 divided by C3 into 100. This is also good. C7 minus C6 divided by C6 times 100, right? So these are the percentage differences, right? So what is the right thing here? Rule of thumb: if your results vary due to the change in drastic amount of elements beyond 5%, 5% is the value. If it is changing beyond 5%, then your results are not accurate. In certain very drastic cases where you have a very complex simulation, you can also go a little bit up till 10%, but not more than that, right? So 5% is the usual rule of thumb. This is not a very complex simulation, right? So 5% is the norm. So what is going on here? From 12,762 to 19,750, when the elements are changing, the results are just changing by 0.7%, which is much more less than 5%. So 12,762 would be the optimal mesh. Let me show you another thing which is important to plot. We want to draw a plot here just to look at the mesh convergence. This is very important. So we want to draw a plot like this, right? A little smaller, right? So what we want to insert in this plot, we want to look at using select data. On the x-axis, we would like to see the number of elements. Yeah, so these are the x-axis nodes. On the y-axis, we would like to see the stress values, right? So what is this chart title? This is okay. This is max stress, or we can remove the chart title because this is for mesh convergence study only, right? Okay. I also need to place something, at least, like format. There needs to be at least a chart, y-axis and x-axis, at least. This is the minimum. So horizontal is number of elements, and the vertical is stress max given in megapascal, right? So if I increase the size of this plot, what do I actually see, right? I see a very clear trend that when the number of elements are increasing, sometimes I want to probably increase the size of this so that it is visually clear, and we want to let's to make it a little larger. So 12 points here, 12 points here, right? So this one I can also make it 12 points, maybe 14 points. This one also 14 points. maybe I can do the bolding so that way and make it all black, right? This is also to be turned to be black in color, that way it is visually clear. Okay, so what am I seeing here? Stress max on the y-axis and a number of elements on the x-axis. As the number of elements are increasing, the result is drastically changing initially. Up till when? Up till about a little bit more than 10,000. Typically complying with the rule of thumb that if you go above 10,000, most of your model results will converge for a very not very complex model. But for a very complex model, it might still take you like till 20,000 or 25,000, right? So after 10,000 ish, like around 12,000 something ish, the results are not changing at all. It's almost a flat curve. That means the mesh convergence has happened. And where has the mesh convergence happened? It has happened from the point from which you are seeing it the flat curve, which in this particular case is the mesh with the number of elements 12,762. So whatever your sizing controls were for this particular mesh, you can retain that and you can just focus with this mesh and run all your simulations at different loadings, or you want to apply all the different kinds of like loads and boundary conditions and whatnot and different orientations. Those all things you can do. Retain this mesh size, because this mesh size we have found out that the results do not change, right, and the results are accurate. So this is what the crux of the mesh convergence study is, which we have learned so far. We have in summary did a lot of hit and trial by changing only the mesh by keeping the loads and boundary conditions constant, right? We create a geometry, we keep the loads and boundary conditions constant, we change the mesh with the aim that we want to increase on the number of elements. And how do we want to increase? Not like randomly. We want to apply sizing controls to make sure that the increase is proper and the mesh is still not very coarse. It is getting more and more fine and much more uniform in terms of transition of the elements. We do not need a big element followed by a smaller element. So if you forget to click a sizing control for one edge, it's going to produce a big element, right? That is going to cause your results to again be inaccurate. So you need a nice transition of the mesh, which we have been able to achieve here. And then using the 6 meshes, the rule of thumb is more than 5 meshes. More than 10,000, once the number of elements increase, what we saw was the result was converging. The DMX did not change at all, and the stress max was initially fluctuating a lot, but then it got a flat curve. So that's where we found out that below 12,762 elements, the results are going to be almost the same, irrespective of how many are the number of elements which you increase, which is perfect, right? So this is as far as our mesh convergence study is concerned. Now what we can do is we get back to this. I want to go back to where this 12,762 was, but I have forgotten in this particular case what my sizing control details are. So it's a good idea to save those sizing control details as well when you're trying to create that mesh. Just write it down below so that you are able to reproduce that at a later stage, right? So hopefully you have learned something today about mesh convergence. So that was the goal. So in the next session, what we are going to talk about is contact. Now we have just been talking about one body. We want to talk about two bodies. We have talked a little bit about two bodies when they're interacting to a certain extent. We want to talk about bodies which are separated or just touching each other. How do you establish contacts in that? So that is also a very important topic, contact pairing. So that is what we are going to learn in the next session, and finally we'll conclude our these lessons on the ANSYS simulations with a very complex simulation where we are going to apply all these concepts which we have learned so far. So please practice mesh convergence study and make sure you're aware of how this is done, right? I'm also going to show in the upcoming session some literature where some published work also does all these same steps to make sure that the simulations are properly done and they're accurate, right? So with that, I would like to thank you all, and I'll see you all again.